Hello everyone. Today in this tutorial we will learn about few aspects of macroscale modeling in PravaH. Macroscale modeling deals with the melt pool dynamics in the laser powder bed fusion process. In first part of this video we will briefly discuss about the input material properties and their significance. In the second part we will discuss the process parameter inputs. You will also learn to create complex scan pattern. Let's create a new project. I am saving it in documents. Inside macroscale model, we have three input sections named material, process, and simulation. Inside material, we have default alloy properties. We have 12 default alloys. Similarly, we have argon, nitrogen, air as a shielding gas. For alloy property, we have solid alloy properties, molten alloy properties, and metal vapor properties. Similarly, we have shielding gas properties. In solid alloy properties, we have molecular weight, density, specific heat, latent heat of fusion, thermal conductivity, absorption coefficient, emissivity, solid to liquid Lie constant, liquid to solid Lie constant. Similarly, for molten alloy properties, we have density at melting temperature, we have solidus temperature, we have liquidus temperature, we have specific heat for molten alloy, we have dynamic viscosity of molten alloy, we have thermal conductivity, absorption coefficient, emissivity, and for Marangoni convection, we have temperature dependent surface tension. Similarly, for metal vapor properties, we have specific heat, heat of vaporization, dynamic viscosity, Prandtl number, and vaporization temperature. For shielding gas properties, we have molecular weight, specific heat, dynamic viscosity, Prandtl number, and density. In solid alloy properties, the absorption coefficient determines how far into a material laser of a particular wavelength can penetrate before it is absorbed. Emissivity defines the heat emission through radiation due to high surface temperatures. Lie constant defines the rate of phase change when critical temperature is reached. Higher Lie constant will give faster conversion of one phase to another. Since Lie constant is based on empirical relation, a calibrated value has been provided. User can change these values to match the available experimental results before going for actual predictions. Since Marangoni effect changes the shape of the melt pool and hence the shape of bed thus formed, user can analyze the velocities in melt pool induced as a result of Marangoni convection by inputting temperature dependent surface tension. Latent heat of fusion is the amount of heat that absorbed when phase change happened. Similarly, in metal vapor properties, we have heat of vaporization. It is the amount of heat that has been absorbed into the system when vaporization happens. Solidus temperature and liquidus temperature. Solidus temperature is temperature at which melting starts. Liquidus temperature is below which solidification starts. We can edit all the fields as required. Also, we have important feature to save the material properties. We can load any alloy properties. We can edit the field and we can click on save alloy by giving a custom name. We will be able to save the alloy for future use. The saved alloy can be seen in default alloys. Similarly, we can save any custom shielding gas using save shielding gas button. We will now go back and we will look into the process parameters. So in process parameters, we have scan pattern, we have laser beam component, XYZ components, we have laser power, we have D4 sigma or spot diameter, we have Fresnel coefficients. Similarly, for powder bed preparation, we have spreader clearance and the spreader velocity. We also have powder site distribution input. For initial chamber conditions, we have preheat temperature, chamber pressure, shielding gas velocity, gas flow angle, initial substrate height, and the substrate clearance at boundary. By using laser beam components in XYZ direction, we can give the direction of laser beam. Currently, we have given -1 along Z and along X and Y we have 0. This indicates our laser is pointed downward in Z direction. Fresnel coefficient defines the multiple reflection of the laser on the melt field interface. Higher Fresnel coefficient means better absorption of laser power at each incidence. Fresnel reflection effect is very important to capture keyhole formation and porosity prediction. We have provided default Fresnel coefficients. User can change these values to match with experimental results before proceeding for actual predictions. To simulate the chamber conditions, we have provided preheat temperatures and chamber pressures. We also have number of scan layers for multi-layer simulation. We will now see how we can generate a scan pattern. We will go to our project location. Inside our project, we have a folder named dataset. Inside dataset, we have three default scan patterns named pattern.csv, 2layer.csv and 3layer.csv. Let's open pattern.csv. Inside this CSV, we have 5 columns. First column is for layer number. Second column is for time. 3 columns are for x, y, z coordinates. And then we have laser on or off condition. Depending on your pattern, you can provide x, y, z coordinates. In this, our laser is moving from 0 to 250 micron B point. And for this, it takes this much time. The time at each laser position can be calculated based on the scan speed. Laser on or off condition tells solver if our laser is on or off when moving to the particular point. Let's say our laser is moving from point A to point B. And for point B, we have on condition. So when moving from point A to point B, our laser will be on. To next point, point C, we have given off condition. So when moving from point B to point C, our laser will be off. So in this pattern, we are printing from point A to point B with laser on condition. Then we have provided a cooling time. For cooling, we take laser out of the domain and we let laser to be there for cooling time. Cooling time we can provide by keeping the laser off for certain time interval. In this interval, we keep the laser stationary or we can move it to the next starting point. For multi-layer, we can repeat the laser position or we can provide new scanning coordinates. The time will be further added to the last layer time. Let's see 2-layer scan pattern. In this we can see we have 2 layers, layer number 1 and layer number 2. The first layer has been finished at this time. By giving small time interval, we have started second layer. At the initial point of the second layer, our laser is in off condition. We have repeated the coordinates and time will be added to the last layer time. Similarly, we can create 3-layer scan pattern. To calculate time, we will use the time from first layer, and then we will use the time from the end of second layer. Plus, we will add small time interval to switch from first layer to second layer. We will copy this formula, and now we have time for third layer. So now we have created a 3-layer scan pattern. We have generated time for the 3 layers. For first layer, we have z coordinate 0.00011, and for second layer, we have z coordinate 0.00022. Similarly, we will edit the z coordinate for third layer. The distance between previous z coordinate and the z coordinate of the next layer should be equal to or more than the layer thickness. Now we have saved this file. We will now upload the scanning pattern. So we have edited in 2layer.csv. So I will select this file and will open this file. Now I will click on visualize scan pattern. So here we can see 3-layer scan pattern. We can visualize it in a 3D. Now we will create a complete new scan pattern. Let's say we have to print this L scan pattern. So we have point A at 0, we have point B where we have incremented in X direction, we have point C where we have incremented in Y direction. So when moving from point B to point C, we have our X and Z coordinate constant and we have changed the Y coordinate. The scan speed between both the point A and B and C is 1.25 meter per second. For creating this scan pattern, we will use the default scan pattern. So I will copy this scan pattern and I will paste it. I will rename it I have given it a name L pattern. So first I will give XYZ coordinate. So for the clearance in a domain, we usually give a higher Z coordinate. From our pattern, we will input X and Y coordinate. So this is our A point, then this is our B point, and then we have our C point. To calculate the time, we will use the provided scan speed. Our scan speed is 1.25 meter per second. And we know the distance between each consecutive point. To calculate the time, we will divide this length by the scanning speed. So this will give us a time at B point. Similarly, to calculate the time at C point, we will add this time in a previous time. Since when moving from point B to point C, we have traveled same distance. For same scan speed, we will have the equal amount of time. Then we will provide a cooling time. So here we have provided a 600 microseconds of cooling time. So when moving from point A to point B, we have laser on, and then from point B to point C, we should also keep laser on in on condition. Then we will provide a small time interval to switch from C point to the point out of the domain. Here I have added a 10 microseconds, a small time interval for moving our laser from C point to the point out of the domain. We can now save this scan pattern and we can visualize it in PravaH. We'll select the file and I will click on visualize scan pattern. Here you can see a L pattern generated. Now we will try it to simulate for this L pattern. I will once again go back and select my material as Ti64. I will save it. Then I will go back. Then I will save the process parameters, and in terminal I will confirm. I will go back and I will click save all once again, and then I will click run solver. So my simulation has been started. After completion, we will be seeing the simulation results. We will now see how we can give powder size distribution input. So we will go inside our project location. Inside dataset, we have default particle distribution.csv. In this, we have two columns. The first column indicates the powder particle size, and the second column indicates the fraction of that particle size. The first column is a radius of particle. So we have a radius 14 micron, 16 micron, 18 micron, 20 micron, 22 micron, and 24 micron. 0.1 indicates 10% of our particle are of 14 micron radius. The addition of this fraction should be equal to 1. We can add more particle sizes and its respective fraction. Let's say we want in our particle distribution we have 24 micron particle size. Let's say in our particle distribution we have 20% of the particle of size to 24 micron radius. So I will edit this to 0.2. Then I will have to check other particle distribution if the sum is equal to 1. Depending on the distribution I have, I will provide other fractions. Let's say for 14 micron radius we have no particles. Now the sum is equal to 1. Similarly, we can add more particles. I can add a particle of size 4.2 micron radius, 42 micron radius, and I can provide the respective fraction. I will save this file. Now I will upload the saved file and click on open. By clicking on save button, it will save all the process parameters. I will once again click on the save all button and I will run the simulation. First, it will generate a CFD domain by generating a mesh. So our simulation has been finished. Now we will visualize the results. First, we will see the powder spreading. So by clicking on show powder spreading, the visualizer will open. So we have a spreader here, and at the middle we have a substrate, and these are powder distribution. So you can see the radius in this scale. We will run this. So this is our final bed. From top you can see it. This is our final bed that we got, depending on what sizes we provided. And it will be extracted in our CFD domain to further simulate the process. I will close this, and we will see the final results. This is our substrate, and then we have a powder spread on a substrate. So this was with 30 accuracy. If I run it, you can see the pattern that we created, the L pattern. So laser has been moved, and resolidification has been happened, and this is the final build. We can visualize the final build part separately. So this is our final build after resolidification. Also we can see the temperatures. So these are the temperatures on the final build after solidification. Also you can see the temperatures on complete part, substrate and the build. So this is it. In the next tutorial, we will see the simulation setting part, where we will be able to set the numerical parameters to improve the accuracy and time complexity of the simulation. We can also visualize the porosity by cutting the build part. So we'll cut it in a Y plane. So this is our cross section, and on this I will plot the solid. So here you can see a white patches, which shows that the solid alpha value there is a low, which means there must be some porosity. We can visualize it by increasing this value. So here you can see there are small pores that has been captured uh, in the built region. If you want to watch more tutorial videos, you can check our tutorial playlist. Thank you.